This set of lectures is on retail electricity pricing and distributed electricity generation. We've talked a bit about some of these topics, but now we will dive into them in more detail. So the agenda for this particular lecture is comparing retail and wholesale electricity prices, real-time pricing, and we will look at Fowley et al. From 2017. So a quick review, retail prices, what are we talking about? These are the prices that you pay as a consumer in your home. These are your utility bills. Retail prices usually consist of two charges, a fixed charge that does not depend on consumption, and a volumetric charge. For example, we would have $20 per month plus 14 cents per kilowatt hour. The $20 per month is used to cover fixed costs, and the volumetric charge is used to cover marginal costs. So to minimize deadweight loss, we set the volumetric charge equal to the marginal cost and used the fixed charge to cover fixed costs, and typically the volumetric charge is much higher than the marginal costs. How are the retail prices set? Retail prices or rates are set by the state public utility commissions. These are set in what are called rate cases, and you, as the public, can go and participate or watch the rate cases. I don't imagine they're very interesting, but you can hear the utility arguing that they need to charge higher rates, and you can hear the lawyers for the city arguing that the rates are too high, or maybe politicians doing that. The rates are adjusted every 1 to 3 years to account for changes in generation costs. Sometimes, though, the part of the rate may adjust automatically in response to fuel price changes. So if you're a natural gas producer, you don't want the retail prices to be completely fixed, because if the natural gas price goes up, you need to be able to pass those costs along to your consumers. If this is the case, those adjustments are done quarterly, and they're more common for industrial users, not retail customers. There's usually three customer types. There's residential electricity customers. There's commercial, kind of like a grocery store or any commercial business. And then there's industrial, places that are using a lot of electricity. Industrial rates are often lower than commercial and residential because they're essentially buying in bulk. Industrial consumers are more attractive for the utility because the fixed cost of the distribution line is spread out over many megawatt hours, which results in a lower average cost. This is because industrial users are using way more electricity than residential and commercial, and so it's just a nicer thing for the utility. And also, they have steady demand. They're running all out most of the time, and they don't have these fluctuations in demand based on when people are home. As we've seen, wholesale prices vary all the time. This graph is showing wholesale price fluctuations over the course of many days, or over about a week. We've seen the daily load curve, so the load over the course of a single day. Wholesale prices are going to change with the daily load or the demand. So the key takeaway here is that the wholesale prices are varying, but retail prices do not vary over time, except maybe quarterly or annually, like we just said. And this is why retail demand is always modeled as completely inelastic. We've been modeling it as a vertical line on our graphs. So we have this disconnect. Wholesale prices are varying, but retail prices are not. Consumers not responding to wholesale prices is expensive. This perfectly inelastic demand leads to volatile wholesale prices because supply must always equal demand. We always need to have enough supply to meet whatever the demand is, because demand is not going to come down if wholesale prices increase. Wholesale price might be $1 per kilowatt hour, but consumers face a marginal price of only 10 cents per kilowatt hour. So there's no incentive for the retail customers to reduce consumption in response to rising wholesale prices. So this is a real challenge for utilities that need to purchase electricity on the wholesale market and sell it. They need to purchase volatile electricity. Well, purchasing electricity on the wholesale market is subject to volatile wholesale prices, but then they sell it at the retail rate, which is fixed. This was the cause of the bankruptcies in California, the California electricity crisis in 2000. The disconnect between demand and wholesale prices increases the amount of capacity necessary to avoid blackouts. Right? We need capacity to meet the peak demand over the entire year. So what are the solutions to this disconnect? We need to make retail prices vary. We need to allow them to change. And so this is called real-time pricing, and it's becoming a viable alternative. So real-time pricing is retail prices are adjusted in real time, or at least hourly, to reflect changes in wholesale electricity prices. So when wholesale electricity prices go up, retail prices also go up, and vice versa. When they go down, retail prices go down. Why don't we already use real-time pricing? It requires measuring electricity use in real time, which we haven't done historically. Is it reasonable to expect customers to respond to real-time prices? So can customers even observe these prices? So the question is, even if we provided the real-time pricing, would customers respond to them? We don't know. Well, actually, we do know, and that's what we're going to talk about. Technological progress is reducing these obstacles. So a standard meter works like a clock. You might have seen these on the sides of your house or other houses. There's small gears inside the meter that move as electricity is drawn into the house. And they're just summing up the amount of electricity used over the course of a month. Then the utility comes in, checks that, and charges you for what you've used. But smart meters are becoming more common. With a standard meter, you can only observe total electricity use since the meter was last checked. You can't charge based on the wholesale price at the time of use, so you're not monitoring use in real time. As of 2014, over 40% of U.S. households had digital meters that recorded use in real time. These are known as smart meters, and these can send information on real-time use back to the utility. Smart meters, appliances, and smartphones make real-time demand responses possible. With smart meters, use can be monitored in real time, and then smartphone apps can display the current price in real-time consumption. So you can look at what the price of electricity. So in this world where real-time pricing exists with smart meters and smart phones and smart appliances, you can look on your phone from wherever you are and see what the real-time electricity price is, and you can decide whether or not to run your appliances based on the electricity price. It makes it easier for households to change consumption in response to price. Smart appliances can also be programmed to switch on and off in response to electricity prices. For example, a dishwasher might run when prices are low. You might set your dishwasher to run in the middle of the night. Less costly for households to respond to price changes. And the biggest will be electric vehicle charging and discharging. So all of these will be programmable appliances that can charge or use electricity at times when prices are low. We're slowly moving toward real-time pricing. It is now fairly common to have rates that are not completely constant. We might have time of day, peak versus off-peak pricing. Fort Collins has this. Peak refers to the times of high demand. I think Fort Collins in the winter is different than the summer. I can't remember exactly what the hours are, but it's probably around 4 p.m. to 7 p.m. or 5 p.m. to 8 p.m. The peak rates are usually much higher to reflect the higher wholesale electricity prices. And then there's also often summer versus winter rates. And summer rates tend to be higher because people often use more electricity in the summer to cool their homes. Many utilities now offer dynamic pricing plans. Dynamic pricing is charging different prices at different times based on market conditions, just like we talked about in the previous slide. Maybe peak period versus off-peak period, or summer versus winter. Uber and Lyft also use a type of dynamic pricing called surge pricing. The price increases if there are more riders looking for rides than drivers. So with higher prices, so essentially there's more demand than there is supply, this causes prices to go up, and with higher prices, some of the potential riders take other forms of transportation, and some of the potential drivers start driving. Real-time pricing is a type of dynamic pricing. We also have what's known as critical peak pricing as well, and these are the periods over the summer probably where demand is expected to be the highest over the entire year. So the highest demand over the course of a year, and it's usually forecasted based on temperatures, because again, the most use from residential customers comes from hot days when people use a lot of electricity to cool their homes. Few consumers currently face dynamic prices though. Even in areas where everyone has smart meters, few customers face dynamic prices. Where plans are offered, few customers sign up, even if they would save money. Some possible explanations: customers prefer the status quo. Customers may not be aware of their plans, and oftentimes with utilities, customers just don't want to deal with them. And so they're gonna, if the utility suggests you should change to this pricing plan, they're gonna say no way. Maybe that's the preference for the status quo, but it might also be anger against the utility for charging them money in the first place. It's difficult to predict the effect of widespread adoption of real-time prices. If all customers face dynamic prices, how will their electricity consumption change? We aren't entirely sure, but we have some ideas, and studies in economics have shed light on this question. The effect of behavior depends on customers' awareness of the program, so they have to know that they're enrolled in this. They have to know that their prices are changing. The ability to adjust consumption, they have to be able to adjust consumption, and then the effects also depends on the actual prices set by the utility. So higher prices are going to lead to lower consumption than lower prices. How do utilities predict how customers will respond? So if you're a utility thinking about changing your price schedule, how are you going to decide what's going to happen to your consumption? Suppose you work for a utility that is considering what would happen if it used time of use pricing for all its customers. Suppose the utility offered a time of use plan and 2% of the customers signed up for it. How would you predict how much more elastic demand would become with respect to the wholesale price under this scenario? So one way to do this is to compare usage for this 2% of customers before and after they start the plan. Did they become more price responsive after they signed up for their plan? Most likely they did. And how much so? And then you might be able to extrapolate those results to the entire customer base, but you have to be careful. Are these customers that signed up voluntarily representative of your entire customer base? Probably not. And so we have ways around this. Experiments are becoming more common in economics. Another option is to run an experiment. For example, we could randomly choose 10% of customers the utility serves, and then randomly assign half of this group to the time of use pricing and half to the usual pricing. This would be called the control group. We can then compare electricity use across the two groups before and after the treatment period. So this is a randomized controlled trial where we are assigning a random subset of the customers a different pricing schedule. And then with randomization, we can extrapolate to the entire customer base. Fowley et al. Takes advantage of an experiment like this. Did Fowley et al. Randomly assign customers to the time of use pricing? No. One of the hurdles to a lot of these experiments is the utility often thinks that customers might be upset if they're required to switch to the time of use pricing. Utilities don't want to upset their customers. It's a common problem when running these types of studies. Instead, they randomly assigned customers to be defaulted into time of use pricing programs. There were three groups. One was allowed to sign up for the time of use pricing, but not encouraged to do so. So if they found out about it, they could do it, but there was no mailers or anything like that trying to encourage the customers to sign up. And this is what they're going to call their control group. There's encouraged to sign up for the time of use pricing. So they're sent out mail or something that says, hey, we're doing a time of use pricing study. You can sign up if you want to. And then there's automatically signed up for the time of use pricing. And they're encouraged to stay in it, but they were allowed to opt out. And they also did the same thing for a critical peak pricing study. Again, the critical peak pricing is just several days over the summer, the ones that are going to be the hottest, and demand will be the highest. The first thing they need to do is check that randomization worked. Random assignment means groups should look about the same on average across the different groups. We have a control group. Their daily usage in kilowatt hours is going to be 26.6 kilowatt hours. The treatment groups, the critical peak pricing and the time of use, these are the next two main columns. They have the opt-in, those that opted in and those that opted out group, or the option to opt out group. You can see that the daily usage across these 5 different groups, the control is 26.6, the opt-in critical peak pricing is 26.8, opt-out is 26.9, time of use opt-in is 26.5, opt-out 26.4. So the point here is that the daily usage and also the other variables in this table across the different groups, they all look fairly similar, which means that the random assignment looks pretty good, and the results from this study can be extrapolated to the rest of the households that the utility serves. The study finds that customers reduce their consumption in response to the treatment. Not too surprising. The top panel is the encouragement group for the critical peak pricing, and the bottom panel is the encouragement group for the time of use pricing. All of the effects for the opt-in and the opt-out are negative and statistically significant. These are in kilowatt hour changes. The stars represent statistical significance, so these are all statistically significant. And you can see that there's a decline in consumption for each of the treatment groups, and this is what the utility would like to see. They can use these estimates to figure out how much customers in the different pricing programs would reduce consumption at different times of the day. Their estimates allow them to evaluate the program. The program worked. Customers reduced their demand during peak hours, but was it cost effective? The benefits, they're going to avoid using some high marginal cost generators during the peak times, so they need to build less capacity to serve the peak hours. You probably also have some environmental benefits because you're reducing consumption. It depends on whether or not people are shifting their consumption from 1 hour of the day to the next, but most likely you have some environmental benefits. There's costs. The costs are the new billing system, supplying in-home devices and encouragement to customers. So installing these devices in every household costs some money. And Fowley et al. Find that the benefits outweigh the costs for both opt-out programs and one of the 2 opt-in programs. So questions to ask yourself. Do you think it's fair for utilities to switch customers to time of use pricing? In other words, we've been on these fixed retail prices for a long time. Is it fair for utilities to now start switching customers to time of use pricing? Are there problems with this? Is it equal for all customers, whether or not they're low income, low users, and high income, high users? Does it matter if utilities make it easy for customers to switch back to standard pricing? They opt out. And the study only lasted from 2011 to 2013. Do you expect the effects they find to still exist today?